Hi everyone, hope everyone can hear me okay. So I'll just give another second just to make sure everyone can join all okay. And that's great that you can hear me, perfect. Well, it's great to see such a great turnout for tonight. So yeah, welcome to tonight. So tonight's meeting is a PhD Showcase annual event. And so here we're going to be showcasing some of the world's leading research within our Institute for the Climate and Atmospheric Science here at Leeds. And so the point of tonight's talk is really just to show off all the amazing talent we've got within our PhD students here at the University of Leeds. So just a quick go over the format for tonight is we've got 3 speakers. They're going to be giving us a 12-minute presentation with 3 minutes at the end for questions. So aiming to conclude around 7:45, 7:50. So please pop any questions in the chat box function, and then we'll get round to a few of these questions at the end of each presentation. Any unanswered questions, just reach out to us and the speakers can try reply in their own time as well. So I'll just give it another little minute and then we'll get going and I'll introduce our first talk. Perfect. So I'll introduce our first speaker of tonight. So our first speaker is Vania Lopez Garcia. She is studying the lower atmosphere over the Central Arctic Ocean. So Vania did her bachelor degree in physics and mathematics and her master's degree in geophysics in Mexico. And yeah, so she's studying the interactions between the lower atmosphere cloud and the surface over the Central Arctic Ocean. So Vania, if you're ready to turn your camera on. And over to you, thank you.
Well, thank you everyone for being with us today. It's my pleasure to be talking with you about the lower atmosphere over the Central Arctic Ocean. My supervisors are Professor Ian Brooks, Dr. Ryan Neely III, and Dr. Barbara Brooks. What's happening in the Arctic that we should talk about? Well, to start, the near-surface temperature is increasing more than twice the rate of the rest of the globe, as we can see in the left picture. And one of the most visible fingerprints of these changes is that there is a dramatic decline in the sea ice extent. This reduction is about 13% per decade in summer. And as an example, in September 2012, we reached a record minimum when it decreased about 50% in comparison to the median of 1979 to 2000. And just last year, we reached a second record minimum. So one of the consequences of these changes also is that the sea ice is getting younger and thinner. And in the last years, the 40% of the multi-year ice has completely lost. So we're approaching to a state that has been called the New Arctic, which will be seasonally ice-free, and in winter we will have ice, but it will be all thin and fiercer. So a better understanding of this New Arctic has been called a grand challenge for the Arctic climate. Additionally, we have problems with models because they have a lot of uncertainties in the Arctic, more than anywhere else, as we can see in the left picture. And one of the reasons might be that they're getting wrong the surface energy budget, which is in part controlled by clouds. And clouds are one of the biggest uncertainties in climate models. As we can see in the right picture, in the Arctic, in the lower troposphere, clouds are being overestimated. But why should we care about all of this? Well, to start, the indigenous people might be at risk because now they cannot rely on their transgenerational knowledge because it's a new Arctic, and due to the sea ice extent reduction, there are new opportunities for shipping. So we need good local weather forecast. Additionally, as the upper ocean is getting warmer and fresher, it may have consequences in the global oceanic circulation patterns. And moreover, it may have links beyond the Arctic itself. Some studies suggest that it may be linked with extreme weather events in mid-latitudes. But an additional problem is that due to its extreme environment, there is a lack of observations. So, motivated by all of this, was developed the multidisciplinary drifting observatory for the study of Arctic climate, MOISAC, which took place from October 2019 to October 2020. And MOISAC is a huge international interdisciplinary Arctic research program that took observations covering a full annual cycle. Its main objective is to develop a better understanding of the coupled system between the atmosphere, clouds, the oceans, the ice, marine biology, biochemistry, all these different links together so they can be better represented in models. It worth nothing that an expedition like this has never happened before. The only similar expedition was Shiva. It also lasted 1 year, and it happened a little bit more than 20 years ago. But the vast majority of other expeditions were in summer and close to the marginal sea ice. So generally, we have a lack of observations, but even more in winter. So it was very important to develop MOISAC so we can understand better the Arctic climate system. There are hundreds of people working in MOISAC, and it had a lot of instrumentation, but for my purpose, I will only talk about the ones that we are using or will use in the future. Very briefly, I will talk about them. And this slide and the next two slides are just illustrative, and the position might not be accurate. So in the ship in Polonster, we have a heliotropic lidar, and we will use it to study the turbulent properties of the lower atmosphere. We also have a callitropic lidar to study wind profiles, and this has a time resolution of 2.5 minutes. We also have a radioson that was launched every 6 hours. In the Med City, we have two micrometeorological masts to study mean profiles of temperature, wind speed, and also turbulent fluxes. We also have a SODAR, again to study the boundary layer properties and wind profiles. And we have another heliotropic lidar. So what we're doing is to study the Arctic boundary layer. And this which is the lower part of the troposphere. And it can be different between winter and summer. In winter, it typically has a surface-based inversion, while in summer, it typically has an elevated main boundary layer inversion, and below it, we can have a well-mixed boundary layer where everything is mixed, and we call this a coupled boundary layer, or we can have a decoupled boundary layer, which means that we have two layers, the cloud mix layer and the surface mix layer, that are being separated by a weak decoupling inversion. That is very important, because if we have this situation, the cloud is decoupled from the surface, and also the materials that might be in the surface, like water vapor, aerosols, cannot go up into the cloud because the mixing is prohibited in this situation. So it's very important to understand correctly the boundary layer structure. And also, and again, the boundary layer is not well represented in models. So what we are doing to study the boundary layer, our first step is to study low-level jets. And low-level jets are common features worldwide. And they are a maximum in the vertical profile of the wind speed. And they are extensively studied in mid-latitudes because these narrow areas of high-speed flow can extend even hundreds of kilometers. So they are very important to the horizontal transport. But also, low-level jets may lead to strong wind shear that might impact the turbulent mixing within the boundary layer, and that's what we're interested in. One of the ways to develop a low-level jet is if we have this decoupled boundary layer situation. So as the upper layer is decoupled, it does not fill the surface, so the wind speed can increase supergystrophically. And obviously, at some point, it will feel the surface friction, so it will reduce. But if this low-level jet is strong enough or shallow enough, the turbulence that might be producing aloft might meet the turbulence that is in the surface. And if this happens, both turbulence meet, we may have a coupled boundary layer. So we started with a decoupled boundary layer and we ended up with a coupled boundary layer. So it's very important to us to study low-level jets. In the right picture, we're just showing a comparison of the big picture for the frequency of recurrence between observations that were made with Radisson in blue and the Era 5 reanalysis in red. As we can see, the vast majority of the time, they don't quite much. Era 5 seems to work better in pre-winter and winter, but not on the rest of the year. And with this, we want to study low-level jets' properties for the full annual cycle, like the wind speed or their height, so we can have an annual characterization of those low-level jets. After that, we want to study the temporal behavior of low-level jet events, how the wind speed is decreasing or decreasing, or how they are changing their height, because this temporal behavior might be related with the turbulence. And for that, we will use Gallium because it has a time resolution of 2.5 minutes, and also the Solar because it has a time resolution of 10 minutes. And we will use them because with them we can study this finer behavior of low-level jets that we cannot study with other instrumentation like Radisson because it has a time resolution of 6 hours, and Era 5 it has a time resolution of 1 hour, for example. So it's very important for us a finer time resolution. And after this, after having a proper characterization of the temporal behavior, we want to study the impact of those level jets on the turbulence of the boundary layer. And finally, we may get to study the Arctic boundary layer properties for different seasons. So that's the path that we're studying in my project. And thank you very much.
Thank you very much, Vania. That was a really great start to the presentation this evening. Really well done. So yeah, I'll just read out a few questions for you to answer before.
Yes.
Okay, so our first question is from Leonard, and he's asking, so in the Arctic boundary layer, is there a growth of the layer due to the heat flux from above the inversion? Is this at the moment to put this in the numerical? Is this at the moment to put in a numerical model?
Actually, I'm not I don't do models, so I don't quite can answer for models. But yeah, the boundary layer is the depth of it is what the turbulent fluxes can get. The depth of the boundary layer is determined by the turbulent fluxes. So if we had a heat flux, we may have a different depth for the boundary layer, but we're not studying what happened above the boundary layer. We only study what happened below it. Mm-hmm.
Perfect. And then just a little question from Ben. Does Mosaic, do they have connections with local communities in these regions, both for their useful input in the project and also to share the results from the research with them?
I don't really know, but I think it would be really useful to have these links with the local communities, but I don't really know how they are gonna share this information and how they have these connections. But certainly, it will be something very useful. Mm-hmm.
Perfect, great. Well, yeah, massive well done. That was a really, really nice talk. I'm sure everyone's clapping in their rooms at the moment.
Thank you.
So yeah, thanks, Vania. That was really great. And we'll move on now quickly to our next speaker of the night. So we've got Paloma Trascasa-Castro, and she is going to be talking to us about the El Nino Southern Oscillation. And so a little bit about her. She is a second-year PhD student, and she's looking at climate impacts of El Nino Southern Oscillation. She did her undergrad in environmental science in Madrid, and now she's doing, and then onto a master's, of research in atmosphere and climate science here at the University of Leeds. And in her free time, she runs an outreach project called the Climate Press, which I definitely recommend you guys checking out. Some really good podcasts on there. And she also enjoys playing music and hanging out with her friends. So over to you, Paloma. I'll let you get started.
Can you see me okay? Can you hear me? Well, I guess you can hear me.
You muted.
Okay, perfect. Perfect, thank you. Hi, everyone. I'm Paloma Trascasa-Castro. I'd like to thank the Royal Meteorological...
I still can't hear you, Paloma.
No?
If you...
What about now?
I've heard other people can hear. Maybe it's just mine.
Yeah.
Can you hear me? Okay. Yeah, I can see the mic moving. Okay. Hi, everyone. Well, thanks to the Royal Meteorological Society for having me today. And I'm going to talk about my favorite scientific topic, which is the El Nino Southern Oscillation, which I'm going to call ENSO from now on. So the first stop of our journey is the coast of Peru in South America. In the past, the communities of the North Peruvian coast were fed mainly by fish. Over this region, the Humboldt or Peru Current, that you can see in the map represented by the arrow pointing north, brings cold water rich in nutrients that attract a large number of fish and birds. In the 17th century, local fishermen realized that the water was unusually warm, the fish species changed, and there was unusually rainy. And in a region like the coast of Peru that is severely hit by droughts, these meteorological conditions were conceived as a gift. And since they occurred around Christmas time, they decided to call it El Niño, which means the child in Spanish. The map on the left shows a typical sea surface temperature pattern during an El Niño event. So as you can see by the red tongue that extends from the western coast of South America to the central Pacific, the surface of the ocean gets a little bit warmer. It can get up to 3 degrees Kelvin, 3 degrees warmer than usual. And then on the right, you can see a spondylus, also known as the thorny oyster, the spiny oyster, or muyo in Quechua. And the spondylus was considered as the red gold for the Inca civilization, and it lives in warm waters. So when local fishermen and people in Peru saw the spondylus on the beach, they knew that El Niño was coming. Now we skip 200 years in history and land over India. In 1877, the failure of the monsoon rains led to severe droughts and famine, killing over 17 million people in India and China. And after these events, meteorologists start to make serious efforts to predict droughts. British meteorologists Charles Todd and Norman Lockyer realized that when drought and very dry conditions occurred in India, that those droughts and very dry conditions occurred at the same time as the heavy floods in Peru. Some years later, the Swedish meteorologist Hugo Hildebrand was looking for what he called atmospheric centers of the action, and found that when atmospheric pressure was very high in Sydney, it was very low in Buenos Aires, Argentina, and vice versa. And then some years later, Lockyer also identified an atmospheric seesaw between India and Cordoba in Argentina. So the idea of the atmospheric seesaw really paved the way for the discovery of the Southern Oscillation some years later. Sir Gilbert Walker was looking for world weather records and found out that different climatic variations across the world were in fact correlated with the Southern Oscillation, which is an atmospheric seesaw between the central equatorial Pacific and the western equatorial Pacific. So sea level pressure is normally very high in Tahiti and very low in Darwin, and that strong pressure difference enhances the flow of the trade winds from east to west. But every 2 to 7 years, that strong pressure gradient weakens, and also the trade winds weaken and is unusually dry in Australia and India. This Southern Oscillation can be quantified by comparing the sea level pressure in Tahiti and Darwin, and is known as the Southern Oscillation Index, which you can see in the time series below. So after decades of research and scientific discoveries, in 1969, Jacob Jerknes finally realized that El Niño and the Southern Oscillation were in fact two components of the same phenomenon that we know as the El Niño Southern Oscillation altogether. So he suggested that in the tropical Pacific, the atmosphere and the ocean were strongly coupled. The plots you can see here are the oceanic part, so El Niño time series on the top, and the Southern Oscillation, which is the atmospheric component on the bottom. And if you compare both indices, you'll see that they mirror each other. So let's recap now. El Niño Southern Oscillation, or ENSO, is a natural mode of interannual climate variability that occurs every 2 to 7 years in the equatorial Pacific and has two phases. The warm phase of ENSO is known as El Niño. El Niño is characterized by warm sea surface temperature anomalies in the central and eastern equatorial Pacific, as you can see in the little map here at the bottom, and deep convection in the central equatorial Pacific. But ENSO also has a cold phase, which is known as La Niña. During La Niña, we have opposite conditions. We have a cold sea surface temperature anomalies in the central and eastern equatorial Pacific, as you can see in the map, and a strengthening of the Walker circulation. So what does this mean? When the Walker circulation gets stronger, we have strong trade winds that are going to push a large amount of warm waters towards the coast of Australia, to the Western Pacific, and it's going to accumulate there in a region that we call the warm pool. So because the ocean is very warm here, we're going to have a lot of evaporation, deep convection, and rain over this region. So normally, the most common way to identify El Niño La Niña events is by looking at sea surface temperature anomalies in the Niño 3.4 region, which is the black rectangle that you can see in the maps. But the isolated Walker cell that I showed before, so the Walker cell, sorry, that I showed before is not an isolated cell, but instead is part of a whole tropical system of interconnected cells that is known as the Walker circulation. And this is very important to consider, because if we have changes in the Walker circulation during El Niño and La Niña events, we're going to, the whole tropical belt is going to experience change in their meteorological conditions. But the scope of the reach of ENSO and its impacts doesn't stay just in the tropics. We can, as I'm going to show now, ENSO impacts can be felt all across the world, and that's why it's called a teleconnection. This is a time series of global mean surface temperature anomalies. So this basically indicates the average of the temperature of the Earth. And well, I'm showing here from 1980 to 2018, and El Niño years are shown in red and La Niña years in blue. And with this plot, I just want to say that every time El Niño occurs, the Earth gets a little bit warmer, and every time La Niña occurs, the Earth gets a little bit cooler. Some very strong El Niño events in the past were occurred in 1982, 1983, 1997, 98, and the last one in 2015, 2016. Let's explore now some ENSO impacts across the world. It's very important to know that ENSO impacts don't occur at the same time in every part of the world. For example, in Europe, we feel the impacts during the winter months, so from December to February. There are many different ways through which ENSO events affect European climate conditions, and I'm not going to get into a lot of detail, but just to mention that this can happen through the changes in the water circulation, through a tropospheric pathway, which is the layer of the atmosphere that is closest to the surface, by leading to changes in climate conditions in the North Pacific, North America, and the North Atlantic. And ENSO events can even alter the stratospheric circulation, which is the layer of the atmosphere that is sit at 50 kilometers up in the atmosphere. An example of this influence is that El Niño events increase the frequency of sudden stratospheric warmings that are normally linked to very cold winters or very cold conditions in Northern Europe. As a general rule, El Niño couples with a negative phase of the North Atlantic Oscillation. That means cold and dry conditions in Northern Europe and warm and wet conditions in Southwestern Europe. However, ENSO events are strongest in India during the summer months. El Niño is generally associated with reduced monsoon rainfall that can sometimes lead to drought, and this reduced rainfall decreases crop productivity. For example, it's been registered that the yield of soybean, rice, wheat, sorghum, and chickpea decreases every time there is an El Niño event. And on the contrary, during La Niña, we would expect more intense monsoon rainfall. But we've known about the influence of El Niño in La India for a long time. For example, the strong El Niño event in 1583-84 led to the failure of the entire water supply in northern India. And that is thought to be the reason why the ancient city of Fatehpur Sikri, I'm going to rest now, was abandoned in 1588, just 15 years after it was built. Moving on now quickly to South America, I just want to say that the events of ENSO here are felt pretty much all along the year, but I'm just showing here the summer months, which in this case are from December to February. During El Niño events, we have drier conditions over northern South America and wetter conditions in the South Brazil, Northeast Argentina, Uruguay, and Paraguay. And during La Niña, we would expect more intense precipitation in northern South America and the south of the Amazon basin. During El Niño events, because there are changes in the river runoff and increased temperatures, we have seen, well, it's been registered an increase in the transmission of malaria, which increases by around 35 and 37% in Venezuela and Colombia after an El Niño event. So ENSO events can be predicted up to 8 months in advance with all the powerful tools that we have here. And this map just shows an example of the projection of the temperature impact of the El Niño event of 2015-2016. That was one of the strongest on record. And as you can see here by the bright red colors, there was no doubt that particular ENSO event was going to hit almost the entire planet. But despite all the projections and the forecasts, this particular event affected over 60 million people around the world. So it's very important to predict ENSO. That's a massive step forward, but there's still a lot of work to do to try and avoid that that amount of people feels the impact. So there's a lot of work to do in terms of adaptation and mitigation. I just want to, well, this is the last part, I promise. So the big question is what's going to happen with ENSO and climate change? The truth is that we still don't know precisely what's going to happen. But recent studies suggest that a warmer atmosphere in the tropics is going to hold, well, we know that a warmer atmosphere can hold a larger amount of water vapor, and that means that in the tropics, El Niño and La Niña precipitation impacts might intensify. So the variability is going to increase, and that means that we might expect stronger El Niño and La Niña impacts. And if the variability increases, that means that they are going to be less predictable as well. But as I already said, there are a lot of uncertainties and many people working on this at the moment. Just another example of ENSO impacts on climate change. Yeah, I'm finishing now, sorry. Yeah, we would expect an increase in fire probability during La Niña in southwest North America and during El Niño in Australia and the Amazon basin. And I just want to conclude by saying that every new study of El Niño contributes to assembly this large-scale jigsaw puzzle, which is El Niño Southern Oscillation. And from my point of view, this is a beautiful example on how all the components of the climate system are strongly interconnected. Thank you very much for your attention. Sorry for spending so much time.
Thanks, Paloma. That was great. Sorry for my little sound issue at the start. That's really great. So we've got quite a big bunch of questions, so I'll try to get a few right now, and then you can answer a few at the end. So first question from Kirsten, that's from Sheffield. So she's asking, which monsoon index would you look at when looking at ENSO impact on India in the summer? So June, July, August.
Yeah, so I didn't perform this study. I just looked at the studies from Lisumi et al. And Servarahu et al. I can forward you these papers, and yeah, I'm not exactly sure about how they measured the monsoon, but they used some kind of yeah. I'm sure they identified when the monsoon was coming, and the monsoon reached its strongest peak, let's say, and they made a linear correlation between monsoon rains and sea surface temperature anomalies in the equatorial Pacific. But I cannot tell you exactly what they used, but I can forward you the studies if you want.
Great, and then I'll just ask one more question from Fiona, saying hello from Hamburg, and thank you for these interesting talks. Do you have any comment on the impact of climate change on ENSO frequency?
Yeah, well, as I said, there's a lot of uncertainty, and we still don't know, so it's not very clear. There's a lot of natural variability involved that creates a lot of noise in ENSO projections, as you might know. So it's very hard to know. Some studies say that ENSO will become more frequent. Some say that they will become less frequent. It's hard to know. But what we do know, despite of ENSO, so even if we don't know what's going to happen with ENSO, we know that the atmosphere is going to get warmer, right? So if the atmosphere is warmer and it can hold more water vapor, we would expect the impacts to get stronger. So if it rains a lot in Peru during an El Niño event, it's going to rain more. But yeah, as I said, I cannot say very precisely, but I hopefully will be able to answer your question in 2 or 3 years. Thanks.
Great, perfect. And then, yeah, in the interest of time, we'll just move on to our final speaker, but Paloma might be able to answer a few questions in the chat, reach out. And so our final presenter today, introducing, this is Yvan Romay, and he's studying the last glaciation. So a little bit about him. He is a second-year PhD student. He's interested in abrupt climate changes in the context of the last glaciation. He graduated from École Centrale Supélec at the Université Paris-Saclay in engineering and theoretical physics. before moving to climate science following an internship at the Berner Centre in Bergen. And he spends the rest of his life cycling, sailing, and being involved in overcomplicated debates about music. And most recently, a avid pancake flipper. So over to you, Yvan.
So yeah, we had some great talks about present and future climate change tonight, and I thought it would be good to finish the night with a talk about past climate change. So that's why I wanted to talk to you tonight about the Ice Age, the last glaciation, and the last glaciation. Why do I want to talk about that? It's because despite being now admitted that an ice age has happened in the past by general public, when we try to get into details of like when was it, what was it, and can it happen again? Well, there are very few people that can answer these questions. So I thought it would be interesting to go through all that together tonight. If you felt upset by saying that no one knows about the ice age, well, you shouldn't, because actually it's quite a recent theory. And before the middle of the 18th century, scientists didn't have any clue about ice ages and more extensive glaciations. And it was residents of the Alps in Switzerland that started to come with theory of more extensive glaciations by observing some marks of ice sheets or glaciers further down the valley than what they observed at the time. So they told that to the scientists that were very happy to have a new evidence of the flood, because surely if boulders were carried down the valley, further down the valley, it was because of strong water flows going through the mountains. But to be fair, at this time, pretty much everything was a good excuse for scientists to find evidence of biblical events. And for example, if the Hamley Hippo, that you should all know about, was found 100 years before, probably had been concluded that it was either carried by the waters to Leeds, or it was probably just when Noah's Ark passed the UK that it fell down the boat. So it took about 100 years for first glaciation theories to be debated and admitted, and 100 more years to have the first records and first reconstructions of the last glaciation to be able to validate these theories. I don't have too much time to talk about the history, unfortunately, but if you're interested in that, I can highly recommend this book by John and Catherine Embry that talks a lot about the history and basically the first climate skeptics. But, well, what we can do tonight, though, is to try to construct our own glaciation theory by looking at all the processes that happen during, to create the glaciations. If we start with the longer time scale, so millions of years, we can come up with what we'll call glacial conditions, which is that continents has to be in the right place, and because the continents have to be in the right place, and volcanic activity low enough so that greenhouse gases concentrations can allow ice sheets to create. So if we put that on a very simple graph, it's a yes or no condition. Either we have these glacial conditions verified, and then we are in a glacial state, or we don't, and we are in a warm interglacial state. Another phenomenon that can influence the amount of energy received by Earth and therefore the global temperature of the planet is orbital forcing. Because indeed, Earth's orbit around the sun has not been constant through Earth history. And Archian quoted out actually at periodicity of a timescale of 10 to 100,000 years. And so that changed quite a lot the insolation received by Earth and therefore the global temperature on the planet. So that's a wonderful drawing I did handmade to try to illustrate that. But basically on top of the conditions, we'll have some oscillations during glacial conditions due to these changes in the insolation. And at last, and I would say the most interesting, is internal climate viability, which is a big word to put all the processes that happens within like years to millenniums. There are quite a lot of of processes that I won't go through. So I won't go through the entire list, but some that you might know are like greenhouse gases forcing, of course, ice sheet feedback, which is the fact that different surfaces reflect different amounts of light and energy from the sun, and in particular, ice reflects most of the energy and absorbs very little. So the more ice you create, the more you reflect this insulation, and the colder the climate gets. But so yeah, as I said, I won't go through the entire list, but one that is quite important in my mind is the thermal line circulation. So the thermal line circulation is basically the global connection of ocean currents being driven by gradients of temperature and salinity. And that's some big conveyor belt, it's called, that is bringing warm and salt to higher and lower latitudes. A good example of an impact it has on present day climate is that it's always like weird to realize that we are at the same latitude than Newfoundland in Yorkshire. And well, I've never been to Newfoundland, but from what I've seen there, it looks pretty cold, at least way colder than Yorkshire. And it is because the UK is on a warm branch of this thermal line circulation, whereas Newfoundland is on the cold branch. So that's the sort of disruption of temperature and climate this thermal line circulation can cause. And obviously disruptions in this circulation can have quite huge impact on climates at the pole. All right, yeah, come back to this wonderful drawing where I tried to add like some new short scale and lower amplitude oscillations. And that's basically it. Like that's all theory of the glaciation. And just as scientists 200 years ago, we know how to find ways to verify that this theory is actually what happened. To do that, we have a couple of what we call proxy reconstructions, so way of reconstructing past climates. And the most important being ice cores, which are basically, cores drilled into Greenland and Antarctica to reconstruct, to have access to temperature, greenhouse gases, and a lot of other data of previous climates. So obviously, this is a huge, great way to have access to this data, but quite incomplete because we only have data over Greenland and Antarctica. So it has to be completed with some other proxy reconstructions, such as marine core sediments or geological evidence of the presence of ice sheets that we can observe by satellites, for example. And so that's altogether creates a good record of what happened, especially during the last glaciation. And if we plot this last glaciation, that's what we get. And if we compare it to the previous drawing I did, it is, I would say, much more complicated for the list. So the whole job of the scientific community has been for the past 50, 60, 70 years to try to understand all these changes, all the climate changes that happened during this past glaciation. So if we try to disentangle these arbitrary climate changes, the first one we can talk about is what we call Dunsgurshger events, which are oscillations, millennial oscillations of climate from cold to warm conditions that happen regularly during the last glaciation. And when I'm talking about arbitrary climate changes, I'm talking about like up to 10 degrees of change in 50 years, something quite dramatic. And the problem is that we have theories about what have happened, but actually we don't know yet what was the actual mechanism that drove these oscillations. The main one being changes of the strength of the AMOC, which is the Atlantic component of the thermal line circulation. But yeah, once again, we're still looking for a good mechanism to explain the entire cycles. Irish events is another hybrid climate change, which is basically iceberg breaking from the ice sheets and being released in the ocean. So carrying cold and fresh water further south and disrupting this AMOC. You can see a nice picture of that reconstructed with potatoes. Once again, when I'm talking about hybrid climate changes, if a rough estimation of the surface of iceberg being discharged in the ocean might be about 5 times the size of the UK, so something quite significant. And at last, maybe the most interesting of all, I would say, and I don't say that because it's my research topic, is the last deglaciation, and basically trying to understand how we went from this cold stage of climate to this warm pre-industrial climate in only 10,000 years. There again, lots of theories. I won't go through all of them tonight, but we still are looking for a good way to explain that. Although, yeah, there are some good video evidence of theories implying squirrels and nuts. A bit skeptical about that, but something to look at for sure. So that's where climate models come into play, because we have quite a lot of pieces of the puzzle by these proxy reconstructions, and we'll have to try to make the links between them. And the climate models are there for that, to try to reconstruct the entire climate of the last glaciation, and to make the links between them. So that's what a lot of research groups are trying to do all over the globe at the moment, by trying to look at some very specific events. For example, for my project, I'm looking at the effect of meltwater on climate, that meltwater from the ice sheets on climate during the last glaciation. But that's like, yeah, the main projects at the moment to try to reconstruct this last glaciation. And yeah, you would ask, why do I care about past climate? And you might be right, but actually, past climate is not only about trying to understand what happened before, but also to try to understand what will happen in the future, because they are. I mean, as I said, we don't have a good theory of what happened there, what drove these hybrid climate changes. And maybe if we were to show that to a paleoclimatologist, he would say, oh, the IMOC, so thermal line circulation, is decreasing. That might mean that we are going to observe a new hybrid climate change. So I'm not saying it's going to happen. I have no idea, actually. But what I'm saying is that past climate, knowing past climate, is a good way to understand present and future climate change. And that is pretty much all I had to say for tonight. So thank you for your attention. And yeah, if you have any questions, happy to answer them.
Really great. Yeah, so we've just got a couple of questions in the chat. So we've got a question from Beth asking, do we have any idea when/if another ice age might occur?
So I would say no, for the same reason that I said, that because we don't understand enough what's driving all these climate changes, we cannot say for sure when will a new ice age happen. But as I showed, like ice ages and well, I mean, I shouldn't say ice ages, glaciations are actually mostly driven by the changes of solar insolation. So what I call the Milankovitch cycle. So by looking at it, we can predict when we will have potentially a new ice age. But I myself couldn't say for sure when will it be, and that's I don't think anyone could say for sure when will a new ice age start.
Cool. And then a second question from Ben saying, how do we use this past information to infer future impacts?
Well, there are a couple of ways to do that. The first one is that observing the mechanism that drove climate changes in the past is a good indication of mechanism that can happen in the future and that could drive climate changes. So understanding them is a good way to understand what will happen in the future. And another way is also that the climate models we're using for reconstructing past climates can be, in a way, there's a way of proofreading these climate models by comparing them to proxy reconstructions. So by transporting that to what predictions we do with model climates with model climates for present climate change and future climate change, we can have like some much more information about all these climate models.
Great, perfect. Well, thank you so much, and another big virtual round of applause. And yeah, so that concludes our final speaker for tonight. So thanks, Yvan. And yeah, so we'll just finish off there. So just again, thank you so much everyone for attending. It's great to see such a big turnout. And so we really hope that we've really showcased just a little bit of the amazing and really diverse, widespread work that's undertaken by our PhD students here at the University of Leeds. Yeah, so just reach out to us on social media if you have any more questions for our speakers. Our next talk will be on March the 16th, and that'll be by Richard Martin Barton, who is an operation meteorologist. And he's just going to be chatting to us about the recent cold weather we've been having in the UK. And yeah, so just a massive thank you everyone for coming, and then a huge thank you to all our speakers and also everyone behind the scenes who've just put in the work. So we've had Michael, who's been our co-chair, Ben, who's been hosting, and also thanks to Eleanor and the rest of the RMet Yorkshire team for organising this. So thanks everyone for coming and had some really interesting questions, and yeah, see you next time.